Hello everyone and welcome back to Series and Applications. This video is on geometric progressions. We'll firstly learn what the key features of a GP are and what makes it different to an AP, before again looking at how we find the nth term and then the formulas for the sum of a GP. After that, we'll wrap it up with a summary, so let's make a start with learning the definition of a geometric progression. What makes a geometric progression, or GP, different to an AP, other than having different names, is instead of adding the common difference to find the next term, we multiply a common ratio. Formally, a geometric progression is a sequence where after the first term, the next term is found by multiplying the previous term by a constant number r, which we call the common ratio. So this sequence here is a GP, because we find the next term in the series by multiplying the last one by 5. So we say the common ratio r is 5. As you can see, these numbers get hella big, hella fast. But GPs don't always have to get bigger. This sequence is also a GP, this time with a common ratio of 0.1, because each term is the last term multiplied by 0.1. If you get a sequence where the ratio isn't obvious, to find r, all that we need to do is, funnily enough, take the ratio of two successive numbers. Mathematically, r is equal to the n plus 1th term over the nth term. So if we were given this GP, then the common ratio would be negative 24 over 4, which is 144 over negative 24, and so on, which equals negative 6. And importantly for a GP, it's common for all terms. So that's what a GP is. We multiply our current term by r to find the next term, as opposed to adding a common difference. You might remember the difference between them by remembering that AP starts with an A, so it's the addition one, and GP doesn't start with an A, so it's the multiplication one. So now that we know what a GP is, let's look at how we can find its nth term. If we obtain the next term of a GP by multiplying it by a common ratio, then just like for APs, we can write its general form. If the first term is A, the second term is A times R, or just AR. The third term is AR times R, which is AR squared, and this continues. So to find the nth term, we need to multiply our first term A by R n minus 1 times. So the nth term of a GP is given by AR to the n minus 1. There's nothing tricky about that formula. Let's look at it in action with a quick story. I don't know about you, but when I was a kid, my chore was getting the mail. In retrospect, it really wasn't that hard, but for the lazy kid that I was, our mailbox might as well have been on the moon. So of course, I wanted to be paid top dollar for my services. I tried to convince my mum that on the first day I got the mail, I would be paid 1 cent. But every day after that, my pay would be doubled. So on the second day, I would get 2 cents, the third day I would get 4 cents, and so on. From memory, she gave me the counteroffer of a killer python every week, and I ate that killer python smugly thinking I'd got the better deal. But had she gone with my payment strategy, how much would I have made on the 21st day I got the mail? Clearly this is a GP, because every day the amount that I'm being paid is being doubled, or it's being multiplied by a common ratio of 2. So the pay that I get on the 21st day is the 21st term of this GP. Therefore, using our formula for the nth term, the 21st term would be A, which is 0.01, times R, which is 2, to the power of 20, which comes out as $10,485.76. I guess my mom knew what she was doing. Now the last thing that we need to look at in this video is how to find the sum of a geometric progression. So let's look at that now. Just like with APs, when we're looking at the numbers themselves, we call it a sequence. But as soon as we add them together, it becomes a series. And again, we can find a really nice formula for the sum. So let me derive that now. Here we have the general form of a geometric series which has n terms, where the first term is A, the common ratio is R, and the nth term is AR to the n minus 1. Now let's let the sum of this expression equal Sn, the sum of n terms. In the last video, we did something really sneaky, and that was we wrote this expression backwards. Here, we're going to do something just as sneaky, but slightly different. We're going to take S, and we're going to multiply it by R. So Rs is equal to AR plus AR squared, and so on, plus AR to the power of n minus 1 plus AR to the n. And now what we do is we subtract the second expression from the first expression. So the left-hand side is S minus Rs. But the right-hand side is A plus AR squared and so on, plus AR to the power of n minus 2 plus AR to the power of n minus 1, minus AR squared, minus AR cubed, and so on, minus AR to the n minus 2 minus AR to the n minus 1 minus AR to the n. And the reason that I've lined these up like this on the screen is that we can see we have plus AR and minus AR, so they cancel out, and plus AR squared and minus AR squared, so they cancel out, and everything cancels out except for our A and our minus AR to the n. So, S minus RS is equal to A minus AR to the n, and if we factorize both sides and then divide by 1 minus R, we get our formula. The sum to n terms of a geometric progression is given by A outside of 1 minus R to the n over 1 minus R, where A is the first term and R is the common ratio. Now we generally use this formula when R is between -1 and 1, or the absolute value of R is less than 1. If R is greater than 1, or R is less than -1, we use this formula. S is equal to A outside of R to the n minus 1 over R minus 1, which is exactly the same as the one above, but with R minus 1s instead of 1 minus Rs. It doesn't really matter which one you use, you get the same answer, but if you use the right formula, you keep the numerator and the denominator positive, and that makes things a little bit nicer. So going back to my payment strategy from before, if I got paid 1 cent on the first day and doubled my pay every day, how much would I have earned in total after 21 days? Well, that's 1 cent plus 2 cents plus 4 cents and so on, which is a GP. Our common ratio R is 2, which is greater than 1, so we'll use this formula. The sum of 21 terms is equal to 0.01 outside of 2 to the power of 21 minus 1 all over 2 minus 1, which comes out as $20,971.51. Let's face it, if you take anything out of this video, if you have kids, don't let them screw you over with maths. You got to be smarter than that. So with that in mind, let's wrap up what we've done here. GPs are sequences where the next term is obtained by multiplying the current term by a common ratio. The ratio R is the n plus 1th term over the nth term, and if that's not constant for all n, your sequence isn't a GP. The nth term of a GP is given by AR to the power of n minus 1, and the sum of a GP containing n terms is A outside of 1 minus R to the n over 1 minus R, if the absolute value of R is less than 1, and if the absolute value of R is greater than 1, the sum is equal to A outside of R to the n minus 1 all over R minus 1. So that's it for this video, guys. Catch you next time!